Hi, welcome to the mole. My name is Mr. Markarian. Today we'll be demystifying the concept of the mole as it relates to chemistry, so buckle up and hang on. It's gonna be fun. The mole is also known as Avogadro's number. Amedeo Avogadro was an Italian chemist, and he did a lot of work with gases that helped people come up with the number of the mole, though he didn't come up with it himself. So we can use the mole for many things in chemistry. If you look at the map here that's showing up on the screen, you notice that the mole is kind of the center of attention in the whole process. And so Avogadro's number, which is 6.02 times 10 to the 23rd, when it comes to calculations, really comes into play in this area here. Whenever you're trying to figure out how many moles you have from how many number of representative particles, we use the 6.02 times 10 to the 23rd. So if I gave you an amount of particles like atoms or molecules and said, hey, how many moles is that? We would use the top as our rate for the problem. So if you're going from moles back to particles, we would use this one. If it's asking you a question about, what is the number of moles in a certain mass of a compound, then we use this one, going from mass to number of moles. Again, in the reverse, if we're going from moles to number of grams, we would use that. And it works the same way for the gases too. So in example number 1 here, the question asks, how many moles are in 1.20 times 10 to the 24 atoms of neon? So you notice we're starting down here with atoms, and we're starting with this number of them. Atoms are representative particles. And so that's our given amount. And remember, the given amount goes in the top left of the equation. So far we have our given amount typed into the equation. Now we just need to fill out the rest. Well, if we're going from particles to moles, we simply follow the arrow from there to there and use this rate, and we'll plug that in. And so the rate's plugged in with 1 mole of neon up at the top over 6.02 times 10 to the 23rd atoms of neon, mirroring what we have here. And so when you do the math in the calculator, you get an answer that is pretty much 2 moles of Ne, and so we'll put that in as our answer. And there we have it. So that is an atoms to moles problem that we can look at there. Okay, let's look at one that's going in the reverse direction. So this next one says, how many atoms are in 3 moles of neon? So now we're starting off over here at the mole, and we're moving this way to representative particles, which are atoms or molecules, and we notice that we have to use this rate. So when we set up the equation, we'll see that that rate is in use. So you notice the way we have it set up here. We have our 3 moles is the given amount, which we had up here. We have moles on the bottom to help cancel out. So we'll go ahead and show that cancellation. And we're left with atoms at the top. And that's what we want in the first place. So we end up with 1.81 times 10 to the 24 atoms of neon. So you simply have to be able to put in the right form of the rate and be able to use a calculator. Okay, in the next example, it says, what is the mass of 1.50 moles of water? And so we're going to look at another part of the mole map here that we have, and mass is here, moles are there. If you're going from moles, which we are, 1.50 moles, we're going to shoot across this way and use this rate when we do that. So when we go to plug in the numbers, we'll have 1.50 moles of H2O. And we multiply and we put in our rate. And on the bottom we should have 1 mole of H2O. making sure to put the unit in the label. And on the top, we put the molar mass of water. Now in class you learned that the molar mass of water can be found by looking at the periodic table. When you add up 2 hydrogens and 1 oxygen, a mole of that equals 18.0 grams of H2O. And so we do the math in a calculator, and we'll figure out here what we can get. And so the answer comes out to 27.0. We'll use 3 sig figs since we have 3 here. And that'll be grams of water. Make sure to put your unit and make sure to let people know it's H2O. That'll be more important when we get to the next unit known as stoichiometry, but it's good to start the habit here. So again, we went from moles to mass using that, which is shown here. And again, the given amount goes there. Okay, for this one, we're going in the reverse direction of what we just did. Now it's asking how many moles, and we're starting off with a mass of 88.0 grams of CO2. So we have the mass. Notice as we go this way, we have this rate, and we're going towards the mole on the map. So we go to write everything in, and we'll start off with 88 grams of CO2 and 1 mole of CO2. If you look on the periodic table and add up 1 carbon and 2 oxygens, it comes out to approximately 44.0 grams of CO2. Remember to always go to the nearest tenth when you're rounding molar masses. And most of you guys can do 88 divided by 44 in your head, but it does come out to 2 when you use a calculator as well. And so this would be 2 moles of CO2. Okay, for this question we are going to use the gases portion of the map. You're going to notice that the magic number, as we call them in chem, is 22.4 liters per mole, and it says at STP. And remember that STP is standard temperature and pressure, and that is 0 degrees Celsius and 1 atmosphere, 1 atm of pressure. So this only works for gases. Don't try to use it for water, even though water can be measured in liters. Solids can be measured in liters too, and we still don't use this. So this is only for gases, only at STP, but it is a convenient way to figure out the number of moles. So this question, again, is asking for moles. We're starting off in liters, which is a volume, and we're going to mole. So our rate's going to be 1 mole over 22.4 liters. So we go to plug in our numbers again. We have 44.8 liters of CO2. And on the top we'll have 1 mole CO2. And again, this is at STP only. And 1 mole at those conditions, or under those conditions, is 22.4 liters of volume. So we do the math on this one. 44.8 divided by 22.4 comes out to 2. I'm using easy numbers here just to show you how to do these. And we have 2 moles of CO2. If you're using the reverse, again, same thing, just flip the rate for that. Now, what we're going to do next is look at some problems that involve 2 steps. So for this problem, it says, how much does 67.2 liters of helium weigh in grams? And so let's figure out where we're starting. We're at volume, which is 67.2 liters. We're going to go to the mole first using this rate, and then we're going to go to mass in grams using that rate. So from volume to mole is 1 step, from mole to mass is a 2nd step. So we just have 2 steps instead of 1 in these problems, but they work the same way. Follow the map, use the correct rates, and go from there. Remember to cancel units. Remember to make sure to put down the unit, the label, the number, and everything will work out every single time. So in this one, again, we start out with the 67.2 liters of HE. I put down the liters of HE there, just like we can see in our rate. But also, I don't really need the map if I understand that the liters here need to cancel with the liters there. And so, it's not a huge issue if we remember that. So those guys cancel out. Consequently, the moles cancel out, and we're left with grams of HE, which we have in our answer. In the calculator, it's 67.2 times 1. You don't have to do that. Times 4, divide by 22.4, divide by 1. Again, you don't have to divide by 1 there. Hit the equal sign, and you should be getting something close to that. So you can actually weigh helium just by knowing the volume of the container in which it's in. Most people think, well, helium's impossible to weigh because the stuff's lighter than air. And that's true, but we have ways in chemistry of weighing things without using an electronic balance, and this is one of them, and it's a key concept you guys want to get down. It gives you the power to do a lot of different things in chemistry this semester, and in further sciences like physics and college chem. Okay, for this problem, and this will be our last one, it says how many atoms of helium are in 67.2 liters. So we're starting out at 67.2 liters. We're making a trip to the mole using this rate, then making another trip to particles since it's asking how many atoms, and using that rate. So again, two-step problem, starting from here, going to the mole, going from the mole to the particles or atoms as we have in our problem, same thing. So let's look at how to set this one up. So on this one, we start out with the 67.2 liters again. This time we're going to make that conversion to the mole using these guys. We'll get some cancellation of units with liters of He canceling. We look at the mole here and the mole here, which cancel. And we're left with atoms of He, which is what the question wants. What you want should always go, again, in the top right. Doing this in the calculator, we get this amount of atoms of He in 67.2 liters of helium. So if you had a balloon that was a 67.2 liter balloon and it was filled with helium at standard temperature and pressure, it would contain that many atoms. You would be able to solve that problem. This is a problem that not many people can do in our everyday lives. And it gives you, again, great power in chemistry to get problems solved. So that's our video on the mole. I want to thank you for sticking it out through these example problems. I know it was a lot. The mole is not an easy concept to get at first. I myself struggled with it in high school initially, and it took a while for me to finally get it down once I realized the purpose of it. And the purpose of the mole is to allow us to figure out things like how much a sample weighs in grams without actually weighing it, to figure out how many molecules are in things like a glass of water without actually counting them, which is an impossible task, and just allows us to work with really large numbers without having to deal with those numbers. And again, just go back to the dozen and the pair. A dozen is 12, a pair is 2, a mole is 6.02 times 10 to the 23rd. And it is a very important concept in chem, and I hope this video was helpful. Have a nice evening.